All right, this is the lesson launch for 3.1.2, Secants to Tangents, or AROC to IROC. And this is a lesson that we went over in pre-calculus that has calculus concepts, but we just don't tell you. And we get to make that connection today with lesson 3.1.1, which is the power rule, and it is the math note that starts off this lesson. So let's go through this and look at the power rule. And the power rule just says that when you have a function x to the n, you just take n, multiply it times the coefficient, and then subtract 1 from the coefficient, or from the exponent, and that becomes the derivative f prime of x. And when we go from AROC to IROC, remember what we're looking at is the function, and let's say it's just like this, and we're looking at the rate of change, average rate of change from a point along x, and we call that h from x, this point of x, to x plus h. And this would be along here, f of x plus h, and this of course f of x. And we look at this is the average rate of change, and we don't care what happens in between. Now, instantaneous rate of change is when we take h and bring it closer to 0, or closer to this x value, and we'll look at some examples here. But the connection is that, say if you have your h here, this gets less steeper for this function, but more importantly, as it gets closer to this value of x here, it becomes basically the slope at this point, or the tangent line, which when you look at the power rule, it's the slope function is what the power rule gives you. And that's the connection between what we learned in pre-calculus and calculus. So how do we apply this? Let's take a look. So for b here, we just multiply the exponent times the coefficient. So f prime of x is equal to 5x, and subtract 1 from the exponent, so it's f5x to the 4. And we say calculus is 80%, or calculus problems are 80% algebra, and 20% calculus. So we need some algebraic manipulations, or just another representation of this, which is x to the minus, or to the 1/2. So now that we can get it into the form of x to the n here, so that we can apply the power rule. And this one here is equal to x to the minus 1. So the question for this is which of the functions below can be applied to the power rule, and you'll find that you can apply it to each one of these, with the exception of this 2 to the x, where x is the exponent. And we'll learn in a later lesson how to apply or find the derivative of that function. So you might not be able to directly apply the power rule, so you have to manipulate it algebraically. So we'll look at another problem. 20 is fairly simple, easy and doable. 21 is just the average rate of change, as well as 22, and we'll go over 22 and you should be able to answer 21. So we're looking at a specific example using 21, and a ladybug travels along a straight line at a distance of 10 t squared in the first t seconds after it starts. So sketch it, and when you do sketch it, it looks like a parabolic function, and there should be a little bit more curvature to that, but it's just a parabola t squared times squared with a stretch of 10, stretch factor of 10. So we're looking at this in the intervals of 3 to 4, 3 to 3.1, and 3 to 3.01. And if you see that h goes from a difference of 1 to 0.1 to 0.01, which means it's just going to 0. So let's look at this. So the function is f equals f of x. Sorry, let me fix that for you. F of t equals 10 t squared. So f of 4 minus f of 3 over 4 minus 3, and so that's just 10 times 16 squared minus 10 times I'm getting ahead of myself. 16 squared should be 4 squared minus f of 3 squared over 4 minus 3, which is 10 times 16 is 160 minus 90 over 1, and it equals 70 millimeters per second. So looking at the second one, it's going to be f of 3.1 minus f of 3 over 3.1 minus 3. So f of 3.1 is 3.1 squared times 10. We get 96.1 minus 90 divided by 0.1, and you're going to get 60.1. I'm sorry, 61 millimeters per second. And now for part 3, 3.01 squared times 10 is 90.601 minus 90, and the difference of 0.01, and this one you'll get equal to 60.01 0 60.1 millimeters per second. And you see, if you get closer to 0.01, you'll see that you're going to be approaching 60 millimeters per second for the instantaneous rate of change. Even though you know the problem doesn't ask for the instantaneous rate of change, you're going to be approaching 60 as you get closer here to that change of 0. So let's look at one other problem. Number 25. And we'll briefly go over this math note, which just goes over how we set up that problem with the average rate of change is basically the function, which is basically the change in y over the change in the x, which is just your slope. And the instantaneous rate of change is as you take that change in the x direction, or h, and take that to 0, it approaches the instantaneous rate of change, or the slope. So describe how the instantaneous velocity I rock can be represented on a distance graph. So you take the slope of the tangent line, and that's how the instantaneous velocity is represented. And using the preceding math notes box to write an expression to describe the instantaneous velocity on the cockroach at t equals 12 seconds. So we're taking the instantaneous velocity, so at t at the 12th second, or 12 plus h minus the speed at 12, and divided by the change h, and of course the limit as h goes to 0. And that would give you the instantaneous rate of change at the t equals 12 seconds. So hopefully that helps. Let me know if you have any questions, put a comment, or send me an email. Thank you.